Welcome back, chemists. Today we're going to talk about how we can speak the language of chemistry. In our first lesson, we looked at the periodic table and reminded ourselves about some properties of the elements. And by now we should know some of the names of the element symbols. You could even spell familiar words with chemical symbols like most of the word chemistry here in front of you. So why do we need to be able to speak chemistry? Because it's a language of scientists, and if we're ever talking about a mixture of something, let's say a very useful sunblock, as I have out here today, we need to be able to communicate with one another about these substances. Sunblock is a mixture of many things. Two common ingredients that I find in this particular one are zinc oxide, ZNO, and a molecule called avobenzone. And those two work together to act as effectively a paint, a physical barrier for ultraviolet rays, and also a chemical substance that, because of its electronic arrangement in the avobenzone molecule, absorbs ultraviolet light and prevents it from doing damage to one's skin. Sunblock happens to be a mixture of a whole lot of different chemical compounds. Some of them we'll learn the names of, some of them we won't, and their function as well. But this is the beginning to how this is really its own separate language. Now, let's start with looking at different types of substances we can name, which brings us back to the periodic table and the symbols for various elements. Starting with ionic compounds, which are made out of metals from the left-hand side, and nonmetals, the right-hand side of the periodic table. Metals can lose electrons and nonmetals can gain electrons, and you form compounds out of those things. And we base the name of a compound based on the names of the elements that make it up. Now the metals, once they lose electrons, they become what's called a cation. The name of the cation is the same as the metal element itself. So sodium becomes sodium cation, magnesium becomes magnesium cation. It's the nonmetals that are slightly different. So let's take a closer look at some of those nonmetals. For example, the halogens, all the way to the right, fluorine, chlorine, bromine, and iodine. They will usually, in ionic compounds, form the 1- charge because then they get a noble gas electron configuration. We'll learn more about that later, but for now it's safe to say they form the -1 charge. So fluorine becomes fluoride, bromine becomes bromide, etc. The chalcogen family, or the oxygen family, they gain 2 electrons. So oxygen, sulfur, selenium. The anion is named oxide, sulfide, selenide. These are ones you should just know eventually as you go through this class. The nitrogen family, let's just talk nitrogen, phosphorus. They gain 3 electrons. Nitrogen becomes nitride, phosphorus becomes phosphide. We could even see compounds with carbon in an ionic compound. Sure, carbon would gain 4 electrons, so carbon would become carbide. And let's not forget hydrogen all the way on the other side of the table. Hydrogen can also form ionic compounds with a metal and gaining 1 electron becoming hydride. So there's a good list, I would say, of the non-metal anions whose names you should know. Let's put that into our rules, and here's the first part of your notes for today. Naming a binary ionic compound, well, that is a metal and a non-metal. And the name comes from cation first, followed by anion second, which usually means metal followed by non-metal. How do you name the cation? It's just the element name. Sodium cation is sodium in the compound, etc. The anion, however, is the root of the element followed by the suffix "ide." What we just saw: fluoride, chloride, bromide, iodide, phosphide, nitride, etc. And you put them together. So NaCl would be sodium ion and chlorine ion. That's sodium and then chloride. So I put those together, I get sodium chloride. AlCl3. It doesn't matter that there's 1 aluminum and 3 chlorines to arrive at the name. That has to do with balancing the charge, but that is aluminum ion and chlorine ion, which is called aluminum chloride. So hit pause for a second and see if you can name the other 4 right now. Come back and check and see how you did. Okay, LiH, that's lithium and hydrogen, so we get lithium hydride. CaS, that's calcium and sulfur, so it becomes calcium sulfide. Magnesium and oxygen, OMG? No, MgO, that's magnesium and oxide. And then Na3N, again, it doesn't matter how many of each one go into the name of a binary ionic, so that's sodium, nitrogen becomes sodium nitride. And that's it for a simple binary ionic. Now I'm exclusively talking about the metals that are all the way on that side of the table, aren't I? What about the ones that are in the middle? Those metals in the middle, like the transition metals, also form cations, but most of the transition metals form multiple possible charges, and there's only a few of them shown in your notes right there. So we follow the same rules as we did for binary ionics. It's still cation first, but this time it's not always just the element name. We sometimes put its charge in a pair of parentheses when there's multiple charges that are possible. The anion is still just the root of the element name followed by the suffix "-ide." So copper and chlorine come together. If it's one of each, that's copper +1 and chlorine -1. How did I know the charge of the copper +1? Well, the chlorine is -1 because it's in the halogens family, so the copper must be +1. You backwards crisscross to make sure the charge is balanced. I call it copper 1 and then chloride. Hg and O, well, oxygen is 2-. That means that mercury is Hg2+ as a result. That's how I can tell from the formula what the charge is. So this is mercury 2 oxide. Notice the 2 in the parentheses refers to the charge of the mercury in this compound, not how many mercury atoms are in one unit. Try the others, Fe2O3, MnO2, PbCl2, and COBr2, and come back and check and see how you did. All right, Fe2O3, that's iron and oxide. Now, oxygen is 2-, so as a result of having 3 oxygens at 2- each, that's a total of 6-. That means I need 2 irons at 3+ each. You could always just backwards crisscross the subscripts. So this is iron 3 and oxide. That's an Fe3+ with an oxygen 2-, and 2 Fe3+ and 3 O2- balances out, and you get no net charge. That's how you figure out the charge of the metal from looking at the formula. MnO2, slightly tricky. Oxygen is -2, and there's 2 of them, so all the oxygens make up -4. That means my manganese is also 4, but on the plus side, so that's actually manganese 4 oxide. PbCl2, the Cl is -1, there's 2 of them, so the Pb is +2, that means it's lead 2 chloride. And similarly with COBr2, the bromine is -1, it's a halogen or a halide, so there's 2 of them. That means I need a cobalt 2 with a bromide. Make a note for yourself that there are some we don't use parentheses for, and it might look like you normally do. Back up to the very first example in today's video, the zinc in zinc oxide is just zinc oxide, even though it's over there in the middle of the periodic table. Aluminum is always a 3+ charge in its compounds, zinc is always a 2+ charge in its compounds, and silver is always a +1 charge in its compounds. So we don't really use the parentheses for aluminum, zinc, and silver in their simple ionic compounds. And they're right near each other in the periodic table. There they are, 3, 2, 1, going from top to bottom, upper right to lower left. So we can never use the parentheses in the names of those compounds. Okay, what about things that are made up of not binary substances, but polyatomics? Polyatomics are clusters of atoms that always have the same formula and charge. They're not a molecule, they're still an ion, and it's something that chemists just have to know the names of. And there's a pretty comprehensive chart in front of you right there from the mercury 1 ion, a very simple polyatomic ion. How is that polyatomic? Oh, it's 2 mercuries put together to make 1 ion. That's the only polyatomic made out of one type of element that you're going to see on this chart. The rest of them have multiple elements. I stand corrected. I see peroxide over there in the lower right, so you should see that as well. They all have names. The rules just combine the first 2 rules you went through, and we throw in polyatomics to the mix. Still cation first, followed by anion, just like any other ionic compound. But this time we might use the polyatomic name instead of the name of the other ion if it's not monoatomic. So looking at the examples, I see Na2SO4. Well, that's a sodium cation, and an SO4 something anion. Actually, I know what the something is because Na is always +1 in the alkali metals. That means SO4 is 2-. I find SO4 2- on my chart, and that is the sulfate anion. So this is sodium and sulfate. Never do I use prefixes to account for how many of the cation or how many of the anion I have. That's put in the formula to make sure the charge balances out, but it never ends up in the name. It's interpreted from the name because we know the charge balances. Then the one below it, that's a K, a potassium ion, and an H2PO4- anion, so a very large polyatomic ion. So we have potassium, and then scanning the chart, and eventually we'll have those memorized. That is the dihydrogen phosphate anion. That's all one thing with a lengthy name, so we get potassium dihydrogen phosphate. Try the other 2, Fe parentheses NO32, and that's an NaClO4. Okay, so we have in part C, we have an iron, and then an NO3 ion, and I can tell what the charge is because the subscript of Fe is 1, that's invisible, but it's a 1. That means NO3 has a -1 charge, and the subscript of NO3 is 2, that means Fe has a 2+ charge. So I have an iron 2+, and a nitrate. That's what NO3- is called. Lastly, we have an Na, a sodium cation, and a ClO4- anion, so that's sodium ion, and perchlorate. If you scan the chart, that's what ClO4-1 is equal to. That takes care of all the ionic compounds. Now, if you flip to the back of your notes, we're going to talk about covalent compounds. Covalent compounds are made of all non-metals now, so we have to actually use prefixes to denote how they're named. It's similar to how we named the binary ionics, but now we have prefixes, and there's a little chart there to show us how many of each element we have. Some special cases, mono is never used for the first element. So if I have N2O, there's 2 nitrogens and 1 oxygen. We call it dinitrogen, meaning two nitrogens, and monoxide. Why not monooxide? Well, the 2 vowels back to back sounds a little bit stuttering, so we drop one of them. It's not incorrect, but you usually see just monoxide. It sounds better. Right below it, N2O5, that's 2 nitrogens and 5 oxygens, so we get dinitrogen and then pentaoxide or pentoxide. I've seen both. I think they're both acceptable for us for now. Try the other 4, PCl3, SO2, SF6, and H2O2. Okay, PCl3, we have 1 phosphorus and 3 chlorines. That is phosphorus trichloride, meaning 1 phosphorus and 3 chlorines. SO2, not to be confused with SO2 anion, some kind of hyposulfite anion. This is a neutral molecular compound with 1 sulfur and 2 oxygens. So sulfur dioxide. Notice we don't say monosulfur because we just don't for the elements in the front of the formula when there's only one of them. We only use it if there's only one of them in the end of the formula. SF6, 1 sulfur and 6 fluorines would be sulfur hexafluoride. And lastly, H2O2, if you said dihydrogen dioxide, you wouldn't be incorrect at first, but no one calls H2O2 dihydrogen dioxide. They call that hydrogen peroxide. In fact, because that is a peroxide, it contains the polyatomic, and we have to just recognize that as we come across other polyatomic containing things. Still considered a molecular compound, even though it contains polyatomic ions sort of buried within it. Lastly, the category we're going to finish up with here is how do we name acids. Again, hopefully this is all a little bit of review from your past chemistry classes. Acids, first of all, we have to recognize as an acid. It looks like an H plus an anion, so they otherwise look just like molecular covalent compounds. And they're named based on the suffix of the anion, of which there are 3 different types of suffix that we've seen so far. We have the suffix ate, such as in sulfate, nitrate, chlorate, pretty much in the polyatomics. When we change that suffix to ic acid, and you'll see what I mean when we do some examples. The second suffix we've seen is the ite suffix, also largely in a lot of the polyatomics, so nitrite, chlorite, sulfite. We change that to an OUS or us acid suffix. And then more commonly the ide, back to the original binary ionics, we've seen the ide suffix. Well, if that's your anion, we change ide to ic acid, and we put hydro in the front of it. So let's look at some examples. If we have HClO4, that's H plus the anion perchlorate. So I think perchlorate, I change perchlorate to perchloric, and I add the word acid, and that's the name of the acid, perchloric acid. Right below it, HClO, that's H plus the polyatomic hypochlorite. So I keep hypochlor, I drop the ite, and I add us acid, and you get hypochlorous acid. Try the other 4, H2SO4, HCl, HCN, and HNO3. Okay, H2SO4, that's hydrogen with sulfate. Notice there's 2 hydrogens because sulfate is a 2 negative charge, so it takes 2 hydrogens to balance out that formula. The sulfate anion is what I'm focusing on though, so that turns into an ic acid, so we get sulfuric acid. HCl, that's H plus a chloride. I drop the ide and I add ic acid. But ide means I put hydro in front. So this becomes hydrochlor and then ic acid. And hopefully you just knew that already, that HCl is hydrochloric acid, a very common bench acid that we have. HCN, similar to HCl, that's cyanide. Even though it's a polyatomic, it's the suffix ide that gives me the name hydrocyanic acid. And then lastly, HNO3, that's the nitrate anion with an H. So I change nitrate to ic acid, and we get nitric acid. So that's how we name acids. That's how we name simple binary covalent compounds. polyatomic containing compounds, transition metal containing compounds, and binary ionic compounds. And there's a lot of practice for you to try, and we will continue to hone this skill as we speak chemistry together this year. Thanks for watching.